So we now move on to module 3, which concerns interpolation and regression. These terms are something that you use all the time, even in daily life. I want you to first tell me what is regression by the term. What do you understand? Thoughts? Or I'll give a more simpler term, curve fitting. What do you understand? Just to poll, what is the existing level of familiarity we have here? Yes.
And I guess you kind of say it's you have a function that you're given, you don't really know what you don't know anything about it, like what it looks like or anything, and you try to make a function that goes along with it.
That sort of describes it. So you have, let's say, a lot of data, but that data could have a size, it could have a million entries. Like you might be measuring some quantity y as a function of x, and you might have had like 1,000 rows of data. Now, the most common or the need for curve fitting is that we don't want to carry around raw data. We don't want you, if you suppose you're in fluids lab collecting data in a particular experiment, pressure versus temperature or pressure versus volume or whatever, you don't want to run around with 100 lines of data or 1,000 lines of data. What you want is a simpler equation or a fit or a function that captures this data, but in fewer numbers, so that it summarizes the entire data set. So technically speaking, curve fitting or regression is a way to summarize data sets using mathematical functions. A very intuitive way of defining it. Now, that is one purpose, to summarize data. Now, we use the phrase connecting the dots all the time. When I say, oh, I connected the dots and figured out something, what am I implying? We're speaking, when you say connecting the dots, what does it mean? No. No, I mean, if you just say one word, that you can't expect that to be the answer. You have to explain. What do you mean by connecting the dots?
Making logical connections.
Making logical connections. What was that?
Drawing the line from one dot to the other.
Okay, thanks for the literal interpreting. Okay, what else?
It means you've understood the underlying information that connects all the.
You are making an inference. If you just open the a picture, which is just a bunch of dots, there is nothing to infer from that. You don't know if it's a cat or a human or some kind of object. Connecting the dot literally means eventually you are inferring something. So the most common purpose of regression and curve fitting is to summarize data sets, but the subtle underlying thing that we are doing is coming up with what is the trend in that data. So suppose you have this say, suppose you have time, or let's say time in month of the year, and then here you have gas price. Okay, so you'll start with, let's say, January of 23, and now it's September of 23. You'll have October, November, and then December. So you have all these months, and for each month you can have an average gas price, and you can have some kind of an inference about how the quantity is trending. The most important application of curve fitting is not only to summarize data, but also to understand what your data is telling you. Does it follow a linear trend? Does it follow an exponential trend? Does it follow a flat trend, which means there is really no relation between the gas price and month of the year? It's been the same throughout this year, let's say, then in that case, it doesn't matter, it means the prices are stagnating. So that statement in the end saying, from this graph, I infer that the price is constant so far in this year. That statement you're making is very powerful, and it is driven by a trend, and that trend is what you get by curve fitting. Suppose that the prices were like this, then you would say the price is not constant, the price is increasing almost linearly. How do you know linearly? Well, you can look at it and say, but if you just were presented a bunch of data, like a table having month and then gas price in dollars, say this is January, February, March, April, May, June, July, August, September. If you were just given a number, you have to actually fit a curve to this, find out what type of a curve it is. It could be a linear curve, it could be a second order quadratic curve, it could be an exponential curve. Depending on what curve is the best fit for the data, you interpret that as the trend of the day. Okay, so that is the big picture motivation to studying regression or curve fitting. It is to understand the underlying trends in your data. Okay, so I'll put that last phrase down. So I said it's summarizing data sets using mathematical functions. That is the verb, meaning that is what you do. The noun is to an understanding or inference from the data. What we do and what it is. So we will try to start with something that is very simple. Okay, we'll start with what is called as a linear fit, which is like saying if you have two variables, I'll call this y bar is like saying y fit, x bar is the value of x used in the fitting, and x and y are the real data. Just some nomenclature that I am introducing so that it's not confusing for you. So when we write it as a table, say suppose we have x and y, and those data points, let's say they fall like this, for example. Literally, you could connect the dots and do something like this. That is like three segments that you connected and used it to, interpolate or connect the dots literally. That isn't what we are trying to do. What we are trying to do is to have a single function or a single straight line that passes through the data that is a reasonable representation of the data. So the purpose of having a linear fit is to have a straight line that is a reasonable representation of the underlying data. That is a reasonable representation of the underlying data. You know from your geometry how many parameters are there in a straight line. How many parameters are needed to define a straight line? Can you give an equation for a straight line?
Y equals against D.
So how many parameters are there? 4. So y equals mx plus b. We'll call again some nomenclature. X is our, let's say, independent variable, meaning you just pick x, independent variable, and y is our dependent variable. B is the intercept, and m is the slope. You can take a pause on writing, all this is just kind of conceptual stuff. I'll give you time to catch up. We don't count these variables as parameters. Parameters is something you select as a value based on some physical condition or some experiment or some situation. These are your variables, okay? So these are not counted as parameters. A straight line has two parameters. It is defined by a slope and an intercept. So you can draw a straight line as say something like this, where this is your slope and this is your intercept. Okay. Now, in here I showed you 4 data points, which are then summarized using a straight line, which has 2 parameters. So you went from 4 to 2. 4 data points summarized using 2 parameters. Just to make sure you understood the idea of parameters correctly, tell me if I write the equation, can you please put your foot in? Thanks. Y equal to a1 plus a2x plus a3x squared. How many parameters are there in this equation? Sorry? 3? The coefficient. That is, if you say this is your independent variable x, this is your dependent variable y, parameters are a1, a2, a3. 3 parameters. 3 parameters. Let me ask you one more example. Y equal to a exponent of b x. How many parameters? 2. Uppercase A and uppercase B. How many parameters? Plus c times exponent of minus dx squared over 2. A, B, C, D, 4 parameters. So you can construct a fit function which is as complex as you want it to be based on your data, and depending on how sophisticated the function is, there might be any number of parameters. In this case, in this example, it's 4 parameters. So before we jump into doing 3 parameter fits like quadratic functions or nonlinear fits which have many parameters, the simplest example we are going to learn today is that of a linear fit which has 2 parameters, slope and intercept. Okay. Coming back, I told you about an example in which there are 4 data points summarized using 2 parameters. That is, look at this data point, that's the circle, the filled circle. Okay. Imagine or understand that the fit is supposed to replace the data point. Once you make the fit, there is no need for you to remember the original raw data. It can be erased from your memory. All you need is this equation, say y equal to mx plus b, which is functionally equivalent to the original data, which I'm going to write xi, yi, and in this case I runs from 1 to 4. Are we together so far? And I see a few yarns. I think we are too slow, that I need to pick up my pace. Maybe it's too easy for you guys. All right. So it's functionally equivalent to the data. Now instead of 4, let's assume that there are like 1,000 data points. Would it matter in the number of parameters? Because whether you have 4 or 1,000 or 5,000, the number of parameters will not change. It's still summarized by a linear fit with only 2 parameters. Okay. So the critical thing is, no matter whether your data set is small or large or extremely large, the number of parameters in your fit don't change. They don't change according to the size of your data. They just change according to the complexity or the trend in your data. Okay. So you have this, for example, that's my erase. I'm going to give you an example with real numbers, but before that, I want to make the concept or illustrate the concept first before we have numbers, okay? So suppose you have x and then y. Say you have number 1, x1, y1, x2, y2, x3, y3, x4, y4. Suppose you have 4 data points and you have a fit y equal to mx plus b, where m and b are real numbers. You take this value of x, plug it into your fit equation, okay, substitute in the fit, substitute into the fit, and you will get, let's say, y1 bar. That is, you can substitute x1 into this equation. Depending on what m and b are, you can get y1, y2, y3, y4. That is like saying, look at this picture here. This is y1. Okay. This is y1 bar. This is y2. This is y2 bar. This is y3. This is y3 bar. This is y4. This is y4 bar. I'll give you time to catch up on the right. So anyone has of late been seeing the YouTube recordings? Is it now readable? Did anyone check it out?
Yeah.
Better now? So just from the picture, the fit is supposed to be a replacement for the data. It's like a equation that captures the trend in the data. What is the ideal situation? You want your y1 bar, the fit value, to be the same as y1. That would be a perfect fit, isn't it? And y2 would be exactly equal to y2 bar, and same for 3 and 4. But in reality, that's not the case, because no data is perfectly what you think it is. You think it's a linear, but there is some noise or some deviations here and there. So there is always a difference between the actual value and the value predicted by the fit. Okay, let's compute that. So we'll compute y1, which is like truth, minus y1 bar, which is the approximation. So we'll say truth minus approximation, or actually a good word for that is model. Truth versus model. y2 minus y2 bar, y3 minus y3 bar, y4 minus y4 bar. Truth versus the model. Now you tell me, how should a good model be, or how should a good fit equation be? What is the attribute or ideal desired characteristic of a fit equation?
You should analyze future model.
It should minimize, it should have minimal deviations from the truth, right? So I will write that statement. An ideal fit, or not ideal, I will say a best fit. A best fit is one which minimally deviates from the truth. All right, we write. Can you also please put your leg inside? A best fit is one which minimally deviates from the truth. Now, which is the truth? Should we just look at y1 only y2, only 3, only 4, or a combination of 1 and 2, 1, 2, 3, or should it be all of them? So it should, okay, shall we say it should collectively minimize the difference for all data. The fit, the choice of your fit should collectively minimize the difference for all the data points. Now, what is good for one data point is not good for the other, meaning if you force your straight line to go through 1, it may not go through 2 and 3. If you force it to go through 2 and 3, it may not go through 1 and 4. So you can't do this by just looking at one member of the population. You have to do this by looking at all of them, or you have to do it holistically. Okay, so how do you do that? Any thoughts? If this is a standard, well-known concept, it's in the textbook. But if you are encountering it for the first time, how would you solve this problem? There are these differences. Okay, here is the problem. You are going to tell me how you will solve it. Y bar equal to mx plus c. Y bar equal to mx plus b. Sorry, mx plus b. How would you select m and b such that the deviations are minimized across the board? Your thoughts.
Would you select the first data point and the last data point?
You are saying you would pick only the first and last. Why only first and last? One second.
My thought is, if you take the first and the last, you have a line connecting those two dots. So in relation, there is somewhere in the middle, some may be over that line, some may be below that line.
There is nothing significant about the first or last. It's arbitrary. So your choice is not based on any kind of specific condition. So that's not correct. Yes.
We could give an initial guess for our M and our B values.
Okay.
And then we could grade them, so to speak, by assigning values relative to the size of each of our trigger models.
So you're saying do this by trial and error, where you give them a particular value, get a set of differences, and maybe square them and add them to get like a global estimate, and keep varying this until that estimate becomes smaller.
You could do that. That's not very efficient.
But is that what you're saying?
More or less, yeah.
Okay, that is one way of doing it. One second, I'll come to you. That's one way of doing it. It is called optimization. It is not. It is somewhat like a search process. You are searching for the correct values of M and B, or the ideal values of M and B. But there are more direct ways to do it, which we'll learn first. What you said, it forms the basis of optimization techniques, which is actually a whole world unto itself. We'll come to that. Yes.
You could average the slopes between each line, let's say from Y1 to Y2, then Y2 to Y3, Y3 to Y4. And also average the intercepts, and you could try to make a line based off of that data.
So what you said, what he sort of said about picking a value of M and B and seeing what the consequences are, you can pick any values of M and B. There is infinite choices. There are infinite choices for you to make. Each one will give you a different value of the deviations. Okay, and before I say what is the kind of like standardized way of doing this, let me write down that expression for a deviation. Okay, so what is the deviation at point 1? Deviation at point 1 is, can you look at the table and tell me?
Y1 minus Y1 bar.
Thank you. Y1 minus Y1 bar Of course, this could be positive or negative. I've drawn it like as though it's negative, whereas here it's positive, so I will square it. And I'm interested in the deviations at all the points, so I'm going to add all of them together. Yn minus yn bar squared, okay? And then I'm going to get a square root of all of this, and I'll call that quantity, or actually, let me not do the square root. I'll just call the sum of these squares as E, uppercase E. I need to minimize E by choosing best values of M and B, the parameters. Before we do the next step, for all of us in agreement or kind of understand and follow what is going on right now, the fit you create, call it a guess, call it a model, call it anything that is like an approximation. That approximation gives you a difference at each data point. We are squaring the difference and adding all of them together, giving it a name called E, and we want to minimize this E with respect to the parameter values. Now recall your Y bar is mx plus b. So this is like writing y1 equals mx1 plus b. So can I say that this E here depends on parameters M and B? Can I say that? If I say that, would you agree? E depends on parameters M and B. And now read this statement. Need to minimize E with respect to M and B. Now bring out your calculus knowledge and tell me the next step. You want to minimize a quantity with respect to M and with respect to B. So what would you do? You will take the quantity, differentiate it with respect to M and set it to 0. Right? And then you will take that quantity, differentiate it with respect to B and set that also equal to 0. You're smiling, what's up? Just so happy.
It's crazy. Yeah.
So each of these partial derivatives will yield one equation each. So that's two equations to solve for two unknowns. And it seems like we just did one module on solving linear equations, right? So you guys must be ready to crush this. So what would you do? So E, let me help you along. I'm not going to do the derivation for you. I'm going to make you do it. E here is equal to, so can I write it as summation I equal to 1 to n yi minus mxi plus b the whole square. If I write this, is anybody confused? This is just a compact way of writing this. Okay. I runs from 1 to n, and as you can see, I went from 4 to generalizing it to n. It doesn't have to be 4, it could be 40 for all we care, just generalizing. So this is your expression E, and to make it very explicit, I'll write it E as a function of M and B. I want partial E over partial M and partial E over partial B, and I want to equate those to 0. So this yields two linear equations in two unknowns M and B, which you can solve for. Can you please try doing this algebra? And I'll also do it with you. So try it on your paper and look up.
What's your least favorite thing?
Say it again.
What's your least favorite function?
Where is the square root?
If you're removed from that one.
Yeah, I decided not to put the square root. I decided we'll keep it as square because when it comes to differentiation, it will be convenient. So what is partial E over partial M? You can keep the summation, okay? Partial E over partial M would be summation I runs from 1 to n 2 times yi minus mxi minus b times what? I should multiply by what? Sorry? You should multiply by xi or negative xi, okay? And then you want to equate this expression to 0. So actually to avoid confusion, I'll write it as partial E over partial M if executed and equated to 0 will yield this. So let's do a little bit cleanup before we move on. -2 can be dropped because the other side is 0. So I have summation I equal to 1 to n xi yi minus m xi squared plus minus bxi equal to 0. We drop the -2 from left side. Yes. Sorry, I'm not able to hear you.
I said something wrong.
Okay, so this is a summation, okay, I'm going to split this and write sigma xi yi, where now from now on, okay, I'll just, never mind. I equal to 1 to n minus m times sigma I equal to 1 to n xi squared minus b times sigma I equal to 1 to n xi equal to 0. Before it gets to before we start saying this again and again, simple question for you. What is this term? Just focus on the summation and tell me what it is.
It should just be x1 plus x2 plus x3 plus x4.
It is the sum of all the x values, right? It's sum of all the x values. So let's build a table. Let's have a table here. Here's your original data, okay? Xi, yi. This is your original data. And then I have x1, y1, x2, y2, and so on, xn, yn. Third request. All right, what is this? This is the summation of all the x values starting from row 1 to row n. Just if you're doing this in Excel, which we will do shortly, is to sum up all these values and get one number here, which goes in here. My point being, it's a constant. Do you agree? It's a constant which can be calculated. What is this?
Square constant, it's just a summation square.
It's the summation of the squares, so I'll add a column and write xi squared, which is just x1 squared, x2 squared, xn squared. And the summation of that is xi squared, I runs from 1 to n. That goes here. And the remaining one is xi yi. I'll open one more column, xi yi, which is x1 y1, x2 y2, xn yn, summation xi yi, I equal to 1 to n. So this is one more constant that goes. So you obviously see that if I just take this to the other side to keep it positive, sigma xi squared m plus sigma xi times b equal to sigma xi yi, and in each case I runs from 1 to n. So this is a linear equation with constant coefficients, the variables being m and b. Are we all together? Nobody's lost? No rescue missions needed? Can you do the same for the other? That is, differentiate E with respect to B and form this equation in this form. Can you go ahead and do that?
Real quick, the second negative go.
I just took it to the other slide. So that
Oh, I see.
So I want you to try differentiating E, uppercase E, with respect to B, lowercase b, and equate the same to 0. And redo these steps to get to a similar equation. So it would be, instead of xi, just -1. So again, drop -2 from the left side, we'll be left with yi minus n xi minus b equal to 0. I'll give you time to catch up writing. You're up to here. Okay, so if I split this summation, first term is yi. It's like summing this entire thing, so I'm allowed to sum each term and then add the sums. What is sigma of yi?
It's just the summation of all the files.
It will be the summation of all the y values, which you can easily compute from, say, Excel, or using Excel, or also manually if you want to. So that goes, the sigma yi goes here. And then what is this? Minus m times, now that not x squared but x, sigma xi, and then b times sigma of one, what is b times sigma of one, or counting b n times? It'll just be n, right? It will be the number of times you count it. So next step, what I'll do is, where is space? Yeah. So I'm going to rewrite this. So I'm going to rewrite this. Sigma yi equal to, or I'll take these two to the other side and start from there. I have m times sigma xi, keep it consistent, sigma xi times m plus b times n equal to sigma yi, where I runs from 1 to n, I runs from 1 to n. That being one of the equations, the other equation is sigma xi squared times m plus sigma xi times b equal to sigma xi yi, I equal to 1 to n. This derivation actually is very simple, but I took a lot of time because the same principle can be applied for polynomial regression, like meaning quadratic or cubic functions. It can also be applied for nonlinear regression. So there is no more magic left here. It's just applying it for each type of fit function. So we did linear now, we'll do quadratic, we'll do nonlinear and so on. What is this? Two equations, two unknowns. Okay, so from here we'll solve for m and b, and you can do it two ways. As it stands now with the symbols, you can apply Gauss elimination to derive values for m equal to something and b equal to something, and that something will be in terms of these coefficients. Okay, you can do that right away. But if you're doing a problem with numbers, these will be some numbers, and you would immediately recognize them as two equations and two unknowns, and you could apply a method of your choice, which could be just using Gauss elimination directly and getting m and b numerically, and you don't have to memorize these formulas. I personally don't like deriving such formulas and memorizing them. I would like to see what the technique is and then wing it. Okay, like there is, you know what to do, you do it. Why are you wasting time memorizing stuff? Okay, so let's do a numerical problem where we'll get up to here, and then you will directly compute these values instead of formulas. Yes.
Like if we were given actual numbers, you can use Gauss-Seidel.
Yeah, you can use Gauss. In fact, this linear regression will have only two parameters. Quadratic will have 3, cubic will have 4. So you'll eventually need to use Gauss-Seidel or some kind of a technique applicable for that. Gauss elimination becomes too complicated.
So would you want to see the derivation of the equation?
Of course not. I don't need to see the derivation. If you had this in your cheat sheet and you just plugged in these values from the table is very important. I need to see these values, and I need to see these going into here, and then you solving it directly. This derivation is for teaching. It's not for you when you face an exam problem. But when we go to the next section, quadratic second order regression, I might ask you to do this on your own and get to this point by yourself, because you know the principle now, you can apply it for quadratic. Okay. All right, let's pick a numerical problem. So instead of dictating the problem, let me just project it on the screen. Okay, so give me a second here. Chapter 17. There we go. Is everybody done writing? Can I project? Yes. So this is an example from the book. Okay, so we are going to attempt this table right here. Okay, so the values are there for us to cross check. Don't pay attention to them now. Just copy these values and we'll try to do it by pencil and paper first and then on Excel.
What's the example number?
17.1. Actually, yeah, 17.1. You know what? Hold it. This is sort of a lame example. Okay, let's find example 17.2, which is much more. It teaches a little bit more. So your independent variable is this. Your dependent variable is this. This is time. You can call it lowercase t, or you can call it x. This is velocity v. You can call it y if you want. This is your x data. This is your y data. Don't worry about these yet. So let's do this problem. This is page number, hold on, 466. So if you are presented with this problem, unless you want to spend time in the exam deriving the equations from scratch, what you should have is the starting point is the equation we derived just now for the two equations and two unknowns, which is sigma xi times m plus, can somebody tell this back to me? NB equals sigma yi, yeah, and then sigma xi squared times m plus sigma xi times b equal to sigma xi yi. You should know this either through your cheat sheet or your memory, or you should be able to derive it. Okay, so this is the starting point for linear curve fitting or straight line fitting, and these values here, in our case x, time is x and velocity is y. That's what is coming from the table. So this is starting point, step 1. Step 2, compute the various terms, compute the various summations that appear in the linear equations. Compute the various summations that appear in the linear equations, which is summing over the x, summing over the y, summing over x squared, and summing over xy. So in your solution, that is, if you're doing this on exam, assume that this table will be printed and given to you. Your x and y are right there. Okay. So what you want to do is start from x, y, x squared, and then xy, squared xy, that's right. Xi, yi, xi squared, xi, yi. So you want to do these summations. And what we are looking for is like a very short table where you put these 4 values, which is what is critical here. If you want to be really systematic about this, you can also add n. In the exam, if I give you a problem, probably there won't be like more than 5 entries. I won't torture you by giving you 20 entries. Okay, just maybe 5 entries. But this table is important. This is what we are really looking for. Okay. So what is sigma xi? Of course, it will be convenient if you did this in Excel. You guys want to just do it for the first 5 rows manually and then do it on Excel? First 5 rows, time 1, 2, 3, 4, 5 seconds alone on paper, and then we'll do Excel for the entire. So what is the sigma xi? Pause, there is don't write, look up. If I want to sum over the x column, 1 plus 2 plus 3 plus 4 plus 5, which is 9, 12, 15. So this will be 15 in what units? Seconds. Keep writing the units all the time. Because when you report your fit constants m and b, the question will ask what is the value of m, which in this case will have real units. You have to report with units. When you do this type of fitting or this type of say writing an equation, those quantities have units, and if they represent something, you have to include the units. So 15 seconds. What is sigma yi? First 5 terms. Okay, 107.8. Is it how many decimal points? I would recommend keeping 4 decimal points in all your calculations. It would be meter per second, whatever the unit of y is. Sigma y will also have units the same, meter per second. So you can say this right away. What is the unit of x squared? Second squared, right? If x has unit of second, or time as unit of second, this is second squared. What is the unit of xi or xy? Meters. Meter per second multiplied by seconds, which would be meters. So kindly evaluate the squares. Case here, so let me write here. So sigma xi squared in this case is 1 squared plus 2 squared plus 3 squared plus 4 squared plus 5 squared, which is how much? 55. 55. So this is 55 seconds squared. Just giving some time for people to actually do the calculation for xi, yi, and then tell.
It's a really big number, right?
Say it again.
It should be a really big number, right?
It should be, because this is like saying
Yeah.
10 plus something like 32.6 plus 69 plus 110 plus 155. Is everybody getting this? No?
I got 376.6.
Seems like a consensus
Yeah.
value. 376.6. And what is N?
5.
N is 5. I think we are all clear about that because we are considering only 5 entities. First row, second row, third row, fourth row, fifth row. Don't be confused by the fact that in this case, the independent variable is also taking values 1, 2, 3, 4, 5. That need not be the case always. It's just a coincidence. Yeah. So N is 5. So now with these 5 numbers, you put them back here and form the 2 equations that need to be solved. I'm going to lift my screen because I don't have space to write.
That's
Okay,
that's 3,766, right? Not 376.6.
that's what I was told. 376, 376.6. So if I substitute back here, that is step 3. Step 3 is to substitute the coefficient and get the equation to be solved. What is that? What is sigma xi? That is 15. 15m plus n is 5, so 5b equal to sigma y, which is 107.8. That is equation 1. And then sigma xi squared is 55 plus what is sigma xi? That is 15 b equal to 376.6. That is equation 2. You can choose any method that you like to solve this. Gauss elimination is simplest here. 2 equations.
55 seconds worth.
What is 55?
Oh, wait, no.
So I'm going to take the first equation, multiply it by 3, a multiply it by 3, and subtract it from the second equation, so that I'll eliminate b. So 55 minus 45 times m plus 15 minus 15 times b equal to 376.6 minus 3 times 107.8. That is 10m equal to 376.6 minus 24, 21, 2, 3. Minus 323.4, which is 2, 3, 53.2. So m equals 0.532.
Should it be 5.32?
5.2. 5.2. 5.32. What is the unit of m? How do you figure out units? So you have v equal to m times t plus v. Pay attention. I'm sure you have seen this in your fluid mechanics class or your mechanics of materials class. This equation should have consistent units on each term. So if this unit is meter per second because it's a velocity, what is the unit of v? Should be meters per second, same as v. What should be the unit of m?
Meters per second squared.
So that meter per second squared multiplied by second will give you meter per second. In other words, this is like a constant velocity. This is like an acceleration. So when you report your answer, you are supposed to report m equals 5.32 meter per second squared. We will definitely dock points if the unit is missing. Yes.
When it comes to the right hand side of the two equations that we have, which the top one is just yi and the second one is xi yi.
Yeah,
Those would have different units, right? Because
those equations would have different units, but if you check what is the unit of x squared, that is second squared, what is the unit of our m? Meter per second squared. What is the unit of xi? Seconds. What is the unit of our v? Meter per second. What is the unit of xi yi? Meters. Isn't it dimensionally consistent?
I was asking about when you add the two equations together for the Gauss elimination, because you end up adding the yi and xi yi, which have units of meters for xi yi and meters per second for yi. On the right hand side.
Right. So the unit of this is meter per second, also meter per second, yes. So you're asking what happens to the dimensionality when we do the Gauss elimination?
Is the -3 like have units of seconds technically or something like that?
Correct. -3 should be 3 seconds times equation 1. That would make it consistent.
Would we need to include that?
Sure, and if I were you, I would have failed this because I didn't think of this in all these years, but good point, yes, you should. That's a good catch. So what he's saying is, when we are doing the Gauss elimination, we multiplied one equation by a constant like 3 and subtracted it from the other equation. We are technically multiplying by 3 seconds and not just by the number 3. Okay. For physical problems, paying close attention to the units is good practice. Okay. So also solve for b likewise. What would be the value of b? I got 5.6.
Yeah.
5.6 meters per second. The 0.6 meters per second. Okay. Give you a minute to catch up writing, then we have to discuss one more aspect of this fit. Okay, so hope all of us have caught up on the writing. Here's a question. All right, you got your raw data. You then created a linear fit. You have evaluated the fit constants. Now, how do we quantify the quality of this fit, or how do we say this is a good fit as opposed to a choice of M and B? Which see, you went through this calculation to get M and B to be a particular value. Okay, this is to minimize the error. you could have just picked random, or you could have just looked at the data and with a gut feel, you could have picked, I'll choose M equals 4.5 and B equals 5, that is a choice. Somebody else could make another choice, so as you can see, there are an infinite number of choices one could make. How would you evaluate objectively, quantitatively, what is the quality of each choice? That is the next question.
The square root of the, just like we did earlier,
Square root of what, sorry?
square root of, y1 minus y bar. After plotting, and then we can square that.
So are you saying that we'll go back to our E? So remember we defined E equal to y I minus mxi minus b, the whole squared summation. Any value of m and b that gives you a certain error, you can tabulate it, and you can say, depending on the value of E, my fit is good or bad, you can make a judgment. Applying some statistical principles, which we will discuss in chapter 6, for just for convenience reasons, I'm not bringing it up here because that will be a very elaborate discussion of statistics. I'm just going to write the error estimate associated with a 2-parameter fit can be computed as, I'll call it S, YX or Y/X. This is the symbol, okay? It doesn't denote division, it's just a symbol. S subscript Y/X, it is equal to E divided by n minus 2 square root.
So that's why. That's the error.
S slash, one second. So SY/X is called the standard deviation of the fit. In general, you want to minimize the standard deviation. I'll give you time to write, just look up. We just did not take the value of E directly. Why? Because if you take 4 data points versus 40,000 data points, this is a summation. So the number of data points is more, which means E will look artificially larger. So you have to first normalize it for the size of your data, which is why you divide by n minus 2. And then why do you divide by n minus 2 and not n directly? This 2 denotes the number of parameters that are involved in your fit, and we'll discuss this in more detail when we talk about statistics. For now, you take it from me that you're dividing by the system of the size of your data set minus the number of parameters you are fitting, which is 2 in this case. If you're doing a quadratic fit, 2 will be gone, it will be 3. If you're doing a 4th order fit, it will be 4, and so on. So this number here for your fit divided by E divided by n minus 2 gives you the error on a normalized basis, which can be compared. So if you had one fit for a data set of size say 100 and another fit for a data set of size 400, this gives you a normalized basis to compare all those fits. Okay, so the quality of those fits. Any quantity that has the SYX closer to 0 is supposed to be a good fit or a better fit, and anything that has a large value of SYX or standard deviation is a poor fit. Okay, so that is the fit or error estimate for a given fit. Okay, so things that should be on your memory or your cheat sheet. This would certainly be, unless you can derive it on the spot, this one, and this formula is something you should be aware of. Can you please go ahead and compute the standard deviation of the fit for this particular problem, for this particular. When you do your table, you should probably keep one more column in the end where you compute yi minus yi bar, which is really this quantity here. This and then square it and so.
Professor,
Yeah,
how did we get 376.6 for XIY?
well, I assume when people did the calculation, that is the number they got. There could be a mistake which we can now check when we do it on Excel. So, but it's not really related to any concept. It's just number punching. We'll reach it.
You took the X value, and then you multiply it by the Y value, and then you took a summation of all of those going down.
That was that your question?
Yes.
Yeah. You take all the X value, like you said, multiply X and Y, and then add them.
Like that, so the first so much and first violence. I have a question.
Yes.
How would I solve for E? Is the yi value the sum y?
1 second. Sorry, what was your question?
So if we want to solve for E, we distribute the summation sign, right? Into the.
No, you don't need to. You will have, if you have n data points in your set, you will have n error values. You just sum them, I mean, you square them and then sum them. That's it. You can add one more column to your table. So I don't know what's going on with my OneDrive. Second here. Okay. Oh. So we are now going to try this on Excel. And next lecture, we are going to try a few more examples, both in pencil and paper as well as Excel. What I would like you to do is bring your laptops. We are going to try Excel and also some MATLAB. And also section 17.2, which is quadratic regression or polynomial regression. I want you to go through it by yourself. It's the same derivation, except there is, instead of two equations in two unknowns, it's going to be 3 equations in 3 unknowns. So I want you to go through the derivation so that I can skip it and just go directly for problem solving. Okay. Read up section 17.2 before coming to class on next class. Tuesday. Section 17.2. Okay. So now let's attempt an example. All right. So what I would like you to do, if you're trying this on Excel, type in the values for the first 5 entries and we'll recheck the numbers using Excel. Okay. So I have my time, which is units of seconds. and then velocity, which is units of meter per second. And I'm going to create the summations that I want. What are the summations that I want? T squared, which has units of second squared. I have V times T, which has units of meters. And then what else? That's it. And then I'll write V fit, and then I'll write V fit minus V original. I have 1, 2, 3, 4, 5. .00. Oops. 16.30. 23.00. 27.5. 31.03. T squared, pretty simple. Go here, square this, and then drag it. And then V times T. V times T. Okay. So then I'll write summations sum there's a 376.6, which is multiplying VT is just multiplying V and T row wise and then adding. And for large sets, it's a useful thing to do, which is to do equal to count the number of rows. This is just like counting how many instances were there. So this is your n, sigma x, sigma y, sigma x squared, and sigma xy.
I have a question.
Yeah.
Is there a command to take that information for the number of columns or number of rows that you'll need? So that way you not have to manually resize the
You can put all this at the top. You can put all this at the top. That is, all this can go. Let's see here. So this is your top row, right? So I'm going to insert a row here, and I'll cut everything from here and paste it here. Yeah. So those who are trying, please try this now. And those who haven't brought their laptops today, please do next time. We are going to do this as well as MATLAB. Okay? Once you learn the technique, MATLAB has so many built-in tools to do curve fitting. It's like child's play. If you know what is inside those modules, you can actually process do a lot of data processing very easy. And obviously, you can replace this data with some other problem, maybe your homework problem or something you're doing for practice, and you can quickly get answers for any problem that you want to do, not just one problem. So to recap, please self-study the derivation in section 17.2. I will skip the derivation, but I'll do example problems. Okay. Yes? Was there a question? No. Okay, so we'll stop here today and pick it up next week. Thank you.